I wanted to begin with basically the direction in which astronomy has gone since Copernicus, which is to depose us from the center. And we've been deposed from the center of the solar system, and the solar system, from the center of the galaxy, and the galaxy from the center of the universe. And I feel that the program that you both are on in terms of studying planets around other stars, exoplanets, and exosolar systems, it's going to depose us from the center of life, which will have a really profound impact. And I wonder if you are thinking about that when you're in this pursuit.
Yeah, I certainly am. I mean, I think to add to what you just said, we've, over a period of a few hundred years, realized that physics is a universal thing. We've realized that chemistry is a pretty universal thing. You can find the same chemistry going on kiloparsecs away out in the galaxy. But what we don't know is whether biology is universal. We have no evidence for it anywhere other than here on Earth. And I think probably the answer is that it is universal. And I think the work that me and Natalie do will hopefully help to understand that and to show that it is, in fact, universal.
And Natalie, do you feel aware of this when you're working? I mean, it's long nights and it's, you know,
yes, I think about it every day. Yes, but interestingly, I'm almost circling around back, thinking that life is so precious. You know, you go out searching for planets like Earth, and of course you always circle back to Earth. And you think about habitability and where life is most likely to reside, and you can't help but realize that it took the universe 13.7 billion years to give rise to this self-complexity, or to this complexity that is my physical self. And while it's true that microbial life is probably ubiquitous because it got a toehold on Earth almost immediately, but eukaryotes, multicellular life, humans, animals, plants, mushrooms, all of those things, I don't know. So maybe it's going to turn out that we are kind of special.
Yeah, so it's sort of a competition between feeling insignificant and feeling extraordinary. Rebecca, you provided this beautiful video from the American Museum of Natural History, and I would love for you to walk us through it, but I also want to emphasize that it's real data. This is not a cartoon.
Thank you. Yeah, so this is a film made by Brian Abbott at the American Museum of Natural History. The idea here is we're flying away from our own solar system, and you can see the orbits of the planets indicated by the green lines. As we move away, the sun has been dimmed down. Now we're going to increase the brightness, so it's the proper brightness of what it is compared to all the other stars. And you can see how bright it is. It completely obscures the planets that are orbiting our own sun if you were to observe them from outside. And this is a huge problem, something I've worked on for quite a long time. Now, as we move out into what we call the solar neighborhood, the little blue circles indicate stars with known planets orbiting around them. So there are other solar systems. And we're going to move out even further. The mission that Natalie has spent a large fraction of her life on found thousands of candidate planets around other stars, and those are the yellow ones.
Yeah, actually, Natalie, I wanted to ask you, there was a time when we had discovered a planet or two, and then there was this watershed. Was that Kepler?
That was Kepler.
Can you tell us about the Kepler mission?
Planet discovery, just as you said, it started out as kind of postage stamp collecting. Kepler was the first mission that could actually, first of all, detect planets as small as an Earth, but also detect them in droves. The technique that we used looked out at the galaxy at a footprint about the size of my outstretched hand, with my arm held extended. And we surveyed about 200,000 stars, found something like 4,500 planets all at once.
I'm sorry to make you reference this, but look how small a neighborhood it is for us. That's our galaxy and that's our backyard.
That's this 100 square degrees, a cone going out about 3,000 light years into the galaxy, which is 100,000 light years across. So it is a relatively small piece of our galaxy, but with 4,500 planets, you can start to study exoplanet demographics. And you can ask yourself the question, how common are planets of different sizes and orbital periods in the galaxy? And what we learned, when you guys go outside afterwards and you look up at the sky, every pinpoint of light that you're seeing is not just a star, it's a planetary system. Because on average, every single star has at least one planet, and the closest potentially habitable planet is expected to be within just 10 light years.
That's insane. So, I mean, we did not know this even 20 years ago. And Rebecca, like, how many stars are there in the Milky Way galaxy? Like, this is...
We're talking about several hundred million stars.
Several hundred billion.
Several hundred million.
And
yeah.
everyone has planets.
Yeah, I mean, I think the statistics show that there are likely far more planets than there are stars out there.
In the entire universe.
Yeah.
That's quite staggering.
In the galaxy. Yeah.
Yeah, just within our own galaxy. And then, of course, there are huge numbers of other galaxies, which are a little harder to look for planets in. But
how far away is the furthest planet we could conceivably see?
Oh, it would be, at this point, with the transiting technique, we've detected them even in the Small Magellanic Cloud, which is a companion galaxy of ours. So you can detect them far away. Whether you can study them in detail, though, at that distance is very questionable.
Now, when I was thinking about this event, I was reminded of this Maya Angelou poem, which I was introduced to a few years ago, called A Brave and Startling Truth. And the opening lines are, "We, this people, on a small and lonely planet, traveling through casual space, I'm gonna get it wrong now. Oh, that's right, I remember now. Past aloof stars, across the way of indifferent suns." It's really staggering. I should actually read it because you need to really look at the poem. And it's such a stunning poem, and I wonder when you're working on this, because sometimes I know, Rebecca, you've talked about particular screws that are really important for building your instruments, and like sometimes it's like there's dust and there's noise, and if you have that moment of poetry, and if you're struck by that sort of sense of existential dread, or is it the euphoria of being connected to the universe?
I think for me, well, first of all, I do experience that dread quite often. Science is a very slow process, as you both know. It takes an enormous amount of patience, lots of failures, and then, times when you're collecting data. For example, I build new types of cameras and put them on telescopes. And the main place I've been doing that is an observatory in Southern California called Palomar. Palomar has this walkway around the outer part of the dome. We call it the catwalk. You're about 50 feet above the ground, and you look out at the night sky, and you see just this ridiculous number of stars. We can only point at so many. So there is a sense of dread, and it's a shot in the dark to find a place that maybe would be similar to this, but I'm also interested in the places that are very different. I think there's something very exciting about the variety of these planets we've discovered.
Do you ever feel, Natalie, that deposing us from the centrality of life, which is sort of how we dominate on this planet, is chilling or euphoric, or somewhere in between?
Neither. Science gives great meaning to my life. It gives me perspective. I waffle between existential dread and euphoria. Hope and despair, like all humans do. That's in our nature. I think a lot about cosmic deep time, both looking back and looking forward. And I want to see this pinnacle of complexity, which you are. I want to see that survive into the deep future, because it took so long to make that complexity. But at the same time, more and more, with kind of this dystopian outlook that we have, I'm not sure that we will. But I've reached a place where I'm okay with that, because I also think about worlds that have existed for 3 times the time that Earth has existed, and I wonder how life might evolve on such a planet, maybe even extincting, rebooting in cycles. And I wonder if a species, or if a planet, if a living world has had the opportunity to do that multiple times, maybe the complexity that arises there is more robust, or I don't know, maybe the pinnacle of life in the universe is in the future.
Maybe the experiment's not random, it gets better and better.
Yeah.
It learns from its mistakes.
We're the beta version.
So let's talk about what is in our solar system. So I just want to kind of go through quickly, you know, our Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Pluto, Io. So here's Mercury. It's our innermost planet. It's a rocky planet. Who wants to take the rocky planets and who wants to take the Jovians? You. Natalie, rocky planets. Talk me through the Rockies. We've got.
Talk you through.
Well, just you know, why are our planets so different? Why is Mercury? You know, Venus is sulfuric acid rains. Why are they all so different?
Why do we look to the left of us, look to the right of us, and there's nobody home? Why is Earth the only apparently living world, at least from a global perspective, where life has gotten a toehold? You know, you have these tuning parameters. You go a little bit too close, you go a little bit too small, you lose your atmosphere because you don't have a high surface gravity, or you boil it away in a runaway greenhouse. And here we are in this sweet spot. And that's why they call it the Goldilocks zone. We need to understand that. You know, as we contemplate life in the galaxy, we have to contemplate the extremes of life. And that means that we learn something about our own planet and about the sustainability of life here on planet Earth. So I want to know more about Venus. Unfortunately, it's a very difficult planet to visit, to land on, because your circuit board just melts into liquid. But we are going to do that. We're going to return to Venus and really understand why our twin planet, Venus is the one that's the closest to Earth in size.
It's full of sulfuric acid and not ocean.
It sucks.
Rebecca, can you explain to us the habitable zone, why that became such an... Here's Jupiter, which is...
Yeah, so...
Oh, no, I'm on Saturn.
Oh, that's
Sorry, I lost track.
So...
We're going to the outer planets now.
I mean, at some level...
Which are not in the habitable zone.
Well, yeah, but I want to point out that at some level, the habitable zone is kind of a load of crap, because, you know, there are these weird moons...
What?
Come on, let's fight.
I'm with Rebecca on this.
Sorry, repeat that.
The criterion for the habitable zone is that a planet is at a certain distance from its star and has enough mass to have an atmosphere and sustain liquid water on its surface. Water is something we know that all forms of life on Earth require. However, orbiting a moon like Saturn or Jupiter, there are these strange ice worlds like Europa, which if there are plans to send things out there and melt through the ice and then turn on the camera and then the fish is looking back at you. So that doesn't fit your habitable zone that we talk about in astronomy, but it may very well be inhabited. So I think we need to be careful about being too constrained on how we think about these terms.
Or define what exactly we mean. I mean, for me, the habitable zone is important because I think about finding planets orbiting other stars that are living worlds. So in those cases, life has to be able to take a global toehold. It has to have a global biosphere in order to be remotely detectable. So in that case, the moons orbiting the giant planets, you know, that's where life is going to exist in a tiny niche.
Right, the moons. That's super
Well, but you bring up a
interesting.
very important point here, which is that our search for life at the moment is based on our understanding of life here on Earth. We have to start from that point of view. On the other hand, taking data on some bizarre planet may lead us to the realization that chemistry is being modified there, like it is here on Earth, by a life form that is completely foreign to what we know. And so I like to keep a sort of broader view about that. But you're right, yes, how do you detect life on Europa from, 10 light years away? You're not going to do that.
This is Pluto, which was demoted as a planet, which I know many of you
It's still
are
a
very
planet.
bitter about.
It's just a dwarf planet, but it's still a planet.
So the interesting thing is that there are so many objects like that in the universe. I mean, there could be life on asteroids, there could be life on moons. This is Io, which is one of the moons in our solar system, which might be more hospitable to life than, say, Pluto or Uranus or Neptune or Jupiter.
Except that
The
Io...
volcanoes.
Io reprocesses its entire surface every 10 years. It's so volcanic. So if you're going to live there, you got to figure out how to move fairly quickly.
No, Natalie, please.
Well, I mean, life needs an energy source. Life harnesses energy to do work, which is what maintains our complexity, makes us so we don't unravel and disintegrate. So there are different kinds of energy that you could harness. You can harness the thermal energy that's inside of a planet. You can harness tidal energy in the case of Io. So yes, I think that life could be very creative and prolific and robust and come up with all kinds of innovative evolutionary solutions.
And we know of extremophiles on the Earth that are metabolizing just hydrogen, which is the simplest thing you could possibly try to metabolize, out of vents in the ocean floor. And so these kinds of extremophiles must be encouraging, in some sense, for us to realize not all life forms are as fragile as we are.
What's crazy about that is that you go to all these weird places on Earth, and I can show you creatures that look like they're from alien worlds, but they're actually not so different. All life on Earth is carbon-based, uses water as a solvent to facilitate all of the biochemistry, and encodes its genetic information in DNA, and uses the same 20 amino acids, even though there's hundreds available. So, life took a very specific pathway on planet Earth, and it makes me wonder, I think that that's probably going to happen elsewhere. Carbon is one of the most common elements that the universe makes. It has special qualities, but I also think that, again, life could find interesting pathways for biochemistry when it's hard-pressed.
So, Rebecca, Natalie's bringing up, chemistry and oxygen and carbon, and people need to be reminded why we say things like, we're stardust. And I think it would be really interesting for you to explain, this is not made in the Big Bang.
Sure. So basically, after the Big Bang, most elements that we're familiar with were not present in the universe. There was this enormous, basically everything was hydrogen, lithium, helium, and a few other small, ridiculous little atoms. The stars in their life cycle process this and change it into much heavier types of atoms, like carbon, oxygen, nitrogen, iron, and then much more massive changes in stars as they blow up and die, give you all the other elements of the periodic table. It turns out right now, like if you look at your hand, many of the atoms in your hand have been through about 150 different supernovae in this galaxy. Now that's pretty cool when you think about it. So we are intrinsically tied to the universe. Now I'd like to believe that the cockroaches are not, because but they're everywhere, and they also last much longer than we have. Right? They also look alien, don't they?
Yes, and we're not sure we're the most successful species. We'll come back to that. But I wanted to talk about this transit of Venus, Natalie, that you shared, because this is a great idea for how to observe planets. Can you talk us through the transit of Venus, what we're looking at?
Yeah, you're going to see, this is actual footage of a situation, a moment in time when the Earth was aligned so that we could see Venus pass exactly over the disk of the sun. And it's a coincidence in nature. Astronomers love to make use of coincidences in nature. That's how we learn a lot of interesting things. And so the idea was that we would use the fact that some planetary systems would be in orbits around stars in the galaxy that were aligned such that their planets would eclipse the host star. We don't see the planet. In fact, almost all of the planets that have been discovered indirectly by observing something weird about the host star that allows us to infer the existence of the planet. In this case, we're measuring the total brightness, and we're seeing a momentary dimming of light that repeats every time the planet orbits.
And we saw this in our solar system, which gave people good ideas for how to look for other planets. In this still, you have a kind of sense of scale. So this is what the shadow that would be cast by which planet on the left?
On the left-hand side, you see a black disk in front of the sun that is the size of Jupiter. And it's about 1/100th of the area. So imagine 100 light bulbs, you take away one. That's the dimming of light you have to measure. Easy, right? But on Earth, which you see as a tiny black speck on the right, is 1/10,000th of the area. So that's a very, very tiny brightness change. We have to have part per million precision in order to see it.
Mm-hmm. And Jupiter, just to let people know, is huge in our solar system. It's almost
10 times smaller than the sun, and Earth is 10 times smaller than that. Yeah.
And Rebecca, I hope this loops, because we're talking slowly. This is exactly what Natalie just said. Can you talk us through this?
Yeah, so this is just a graphical representation of that. You're looking at a distant star, which in this case on the top is resolved. When we look at distant stars now, we can't really resolve them, except with a few special techniques that I'm happy to talk about, but not tonight. So imagine the planet is moving there across the star, and on the bottom you see a plot of the brightness of that star, which in your telescope is just a point source of light. You just see it slightly dim in brightness and then come back up. And from the shape of that curve, how quickly it drops and how long it lasts, you can determine all kinds of parameters about the planet. For example, what is its radius? You can look at it in different colors and determine, well, differences in that curve will tell you different properties of these planets. So we can learn quite a bit from this.
Isn't it amazing that every single planet orbiting every single star is casting a shadow out into space?
It is amazing.
And we're catching those shadows.
And we're somebody else's exoplanet.
That's
Somewhere else, they're looking back at us, and we're
and
that
seeing our
tiny
shadow.
dot. And it's that tiny one that, as you said, would be very hard to detect. And then there are other ways that we detect the exoplanets.
Yeah, so this animation is showing so basically the planet and the star orbit their mutual center of gravity, which is not necessarily in the middle of the star. The planet and the star have a relative mass difference, by which I mean that the star itself is also orbiting the center of mass of that solar system. It could be outside the star, and in fact, in our own solar system, sometimes it is. That means the star is wobbling around. And if you observe a star, you can't even see the planet, but in this cartoon you can. As you watch the star along our line of sight to that star, you can see it's moving a little bit toward you and a little bit away from you as a planet orbits that star. Well, the center of the gravity. So the star itself is also moving around. And that's what's represented on the bottom. If you take a spectrum of a star, spread the light out into its constituent colors, you'll see all these little lines that are due to various features in the atmosphere, atoms or sometimes molecules, that will shift backwards and forwards. And we can measure this very precisely. And my current project is in fact doing that at a precision where we hope to be able to detect something the size of Earth. I'm not saying Earth-like, but the size of Earth around a very low mass. It's the most common type of star in the universe.
Yeah, these velocities are really tiny. Well, it depends. Yeah. So the very first planets that were ever discovered were from this method, and the star itself was moving with a speed about like a car driving down a highway. And today we've got technology that can measure speeds of the wobble that are about a walking speed. But if you want to find a true Earth-Sun analog with this method, the star would be moving at the speed of like a ladybug crawling across the stage. That's what we're actually working towards. We're working to build technology to have that sensitivity.
Now, how many exoplanets have been discovered so far?
Ooh, about 4,500.
About 4,500, and they're all within about what distance from the Earth?
So the Kepler field of view, looking at this one fingerprint, stretched out about 3,000 light years. Now there's a mission called TESS, which is doing an all-sky survey focusing mostly on the stars that are nearest to us. So that mission has also found many thousands of candidates that are slowly being confirmed. They tend to be closer.
So we're seeing these planets as they were 3,000 years ago.
And
just as a reminder, the furthest tip of the galaxy, light would take about 100,000 years to get to. So we're still in our backyard.
That's right.
Solar neighborhood.
Very much so, yeah.
Solar neighborhood.
The other
Solar neighborhood.
I mean, there have been some planets detected far closer than that, with a method in which you're directly imaging the system. So you have to, in order to do this, you have to block out the light of the star As you might remember from the video at the beginning, if you look at a particular solar system, the star is so bright that the glare just prevents you from seeing anything. Kind of like, I can't see any of you right now, just a few people in the front row. But if I go like this, I can see you. Oh,
You have
hi.
too many stars up there. You need a multi-coronagraph.
So we have been able to do this, and it's beautiful. You can actually see these planets move around their stars, and then you can actually, for each one, take their own spectrum and figure out what is the chemical composition of them.
So this.
So those are not 100,000 years away, but more
Right.
like tens of years away. Yeah.
Right. So we're seeing them as they were 3,000 years ago. And this, Natalie, this is an artist's illustration, but of a planet that was actually discovered. Can you tell us about this planet?
Yeah, this is Kepler 10. It has a very special place in my heart because I saw the evidence of this planet in the first 10 days of data that Kepler collected. And it was the planet that really told me that Kepler was going to be successful. But it's also special because of its properties. So this is a planet that's orbiting a star very much like our sun, but about double its age, so maybe 11 billion years old. Life could have evolved much longer on planets orbiting this star. But this particular planet is orbiting its sun once every 20 hours. So it's being scorched by the central star. It's orbiting very, very close. That's what Kepler's laws tells us. 20 hours means a short orbital period. The star-facing side has temperatures in excess of that required to melt iron, not just rocks, but iron at standard temperature and pressure. So this planet has an ocean bigger than the Pacific Ocean, but it's not liquid water, it's molten rock. We know a lot about this system. This was our first rocky planet discovery. How do we know that? Because with the transit method, we got its radius, as Rebecca described, and with the Doppler method, you get its mass. And if you have mass and radius, mass divided by volume is density, and that's how you know that it's a rock. So it was very exciting as our first unequivocal rocky planet orbiting another star in the galaxy. Very exciting discovery.
Now, do you, Rebecca, think that in those conditions that the emergence of life is viable, or are you agnostic?
I'm agnostic. I mean, like I said before, I think, in terms of the life that's in this room, we wouldn't be very comfortable there. But on the other hand, if you look at the history of Earth, as Natalie pointed out, the moment life could exist here, it did. And so in a sense, you figure that's a natural outcome of a certain circumstance. However, the Earth also had some pretty violent past periods where it was, like that, in the Hadean period, for example, early on. But perhaps, I don't know, I'd like to leave it open in the sense that I don't know, and I try to avoid biasing my thought based on only what we know here on Earth. To me, saying that, okay, let's go look for life out in the universe, but base your idea of what life is on one example would be like in music theory saying, okay, I want to understand all of human music by only studying Elvis or Chinese opera. You wouldn't have any idea what the range of music was.
Mm-hmm. Now, it is true that life obviously emerged on Earth, but it waffled for a long time. There was at least 1 billion years or more where single-celled organisms didn't progress.
Well, the oldest life that we have discovered is about 3.84 billion years. So as soon as the surface of the Earth was originally molten, because planet formation is a very violent process. As soon as the surface cooled down enough, we had oceans, and there's some evidence of this in like zircon crystals or something, that the isotope ratios say that there was an ocean very early on, and it seems that as soon as we got an ocean, microbial life developed. So it seems that microbial life gets kick-started relatively easily. That's why I think if I had to posit a guess, and I don't know, but if I had to posit a guess, I would say that microbial life is going to be ubiquitous in the galaxy, but not the eukaryotes.
Not
Those
the eukaryotes,
took
yeah.
2 billion years
Yeah.
before that evolutionary innovation was created.
And there are arguments, and they're still contentious, that maybe that was a single odd event, that many times single-celled organisms tried to merge, to progress to multi-celled organisms and failed and killed each other. And then there might have been a singular merger that led to a metabolically favorable organism. And do you think, Rebecca, that it's possible that that's a roadblock to multicellularity and complex life?
It very well could be, but another really fascinating question, something that I've been interested in since I was a kid, is it possible that life, even monocellular life, evolved on Earth in separate places, completely disconnected from each other at the same time, or over millions of years? Or are there areas in the Earth right now that have been isolated long enough, but they have another form of life in it, probably based on carbon? I mean, carbon is a wonderful atom. It forms all kinds of cool molecules, unlike many other atoms in the periodic table. But if you could prove that there are multiple origins of life here on Earth, forget about these exoplanets, that would be a fundamentally important discovery. And I think it would tell us the answer, that of course we're not alone. I mean, I know that's the answer, but I think it would find out that life actually arises very easily.
Let's look at some of these other Kepler systems. Natalie, tell me, do you want me to keep flicking, or you want to talk about each one?
Well, one of the takeaways from the Kepler mission is that the diversity of planets in the galaxy far exceeds the diversity of planets in our solar system.
Yeah,
we found...
Oh, no, please, go, sorry.
There's a lot of exotica. Starting with, this is actually not a Kepler discovery. This is the first exoplanet orbiting a normal sun-like star that was discovered in 1995 in Florence, Italy. I was a young graduate student at the time and just happened to be at the conference where Michel Mayor announced this discovery, which led to the Nobel Prize a couple of years ago. But it was really remarkable because it's a planet the size of Jupiter orbiting its sun, something like 8 times closer than Mercury does, orbiting its star 8 times closer than Mercury does our own sun. Very surprising. Turned planet formation theory kind of up over on its head. So it turns out that even though these were the very first planets that were discovered, they're actually not that common in the galaxy. And Kepler showed that. This is an artist's... Oh, sorry, I was looking at the wrong slide. This is 51, the artist rendering of 51
They're just pretty
Peggy.
pictures.
Yeah, sorry. So you can see this kind of Jupiter-esque type of surface, but just being blasted by its star with radiation, and of course that changed the internal structure of the planet. And really what this taught us is that the planet formation process is also very dynamic. Planets that are forming are interacting gravitationally with one another and interacting gravitationally with the disk and moving around. So when we see a planetary system, even our own, it's not necessarily the same as it was when it first formed.
Now, Rebecca, I've heard you talk a lot. I'm just going to sort of show, these are all artists' renditions.
You want me to shut up?
What was that?
You want me to shut up?
No, I want you to talk. I want you to talk, baby. These are artists' renditions. We can't resolve, as you said, take pictures of it. But we can use the other techniques that were mentioned earlier. But it is interesting that as varied as our own planets are in our solar system, it seems that the exoplanets are even more varied, as though nature tries every physical possibility.
Yeah, and this is what I think is so cool, because even though we can't quite do the Earths yet, or Earth analogs, and look for life, although we know how to do that. We've known for 25 years how to do that. We just need, $50 billion would do it. Well, I think that's worth it. Anyway, but what is also really fascinating is just studying this huge zoo of these things. And we're starting to realize that they may be more related to each other than not. We like to classify things. This goes back to the Bible. Name everything, and therefore you have control over it. Scientists do the same thing, and sometimes those names lead to biases in how we think about what we're doing, what we're studying. And I think the exoplanets are a perfect example of this, because we try to classify things as, oh, here's an Earth-like planet, here's a Jupiter-like planet, here's a Neptune-like planet. In fact, most of the things we've discovered are nothing like those planets. They're somewhere in between, and I think that's very exciting. It's not really tied into the search for life, but it's understanding where we are in this universe, and you know, what does this planet mean? What does our solar system mean?
It makes you think about evolution in general, that evolution isn't just pressures and forces, it's also accidents. And it's also trying experiments over and over and over again until something catches. Natalie, you wanted to talk about this planet.
Yeah, Rebecca already alluded to this, but so Kepler goes out, finds 4,000 some odd planets, and lo and behold, the most common type of planet that was found was something that we don't even have in our solar system. So imagine our solar system. Janna did the roll call earlier. You've got the small rocky things orbiting close to the star. You've got the big gas giants orbiting far away from the star. And there's a big disparity between those two populations. And there's nothing in between in terms of size. But the most common type of planet in the galaxy is exactly that. It's like this gray area in between that we don't understand. And it has significant implications for habitability, because we don't know if these are scaled up Earths with just additional real estate for life, or if they are planets like Neptune that were plunked down at a shorter orbit that had their envelope stripped. Maybe they look like this blue orb that you're seeing. Maybe it's an ocean world. Maybe there's such thing as too much water on a planet. I don't know. Sequestering away all of the heavy elements that you need to build complexity. So these are all open questions. And as Rebecca said, we don't even know what to call these planets. Are they super Earths or sub-Neptunes or a whole bunch of things in between?
We can keep cycling through the range of varieties, but I think all it tells us, if you've seen one planet, you've seen one planet.
Yeah, exactly.
And there is this sort of idea when we think about the emergence of life, besides the possible blockage to multicellularity, which is that we're one of the only species on this planet that actively manipulates its environment, aggressively manipulates its environment. Not just fire, not just clothing, not just shelter, but we explore and we build things. And there's really no clear argument that that makes us a successful species. In fact, it might be quite the opposite. I think it would be fair to say we're the only species on the planet that is capable of intentional self-destruction. And I wonder if you think about that. Like, are we looking for life, or are we looking for intelligent life? And if it's the latter, is it possible that any species that actively manipulates its environment is doomed to failure in the way that we might be?
Well, I would put this in a different context. When you say successful species, I'm not entirely sure what that means. I mean,
I was only thinking about duration on the planet,
well, okay,
to be honest.
but I would say there are other measures of success. For example, this species of ours has achieved an incredible ability of thought, music, literature, art, and science. Science is one of the most powerful forms of thought ever created. I think that is a huge success. And I think, you know, given all the problems that we have here on Earth, you know, climate change and stupid fascist idiots all over the place, we'll overcome this crap. You know, we will. And I'm more optimistic about that. Mm-hmm. Homo sapiens have been around, for about 2 million years, 1 to 2 million years.
Is it that long?
Mm-hmm. Yeah, but over 4.5 billion year history of the Earth, that's not very long. However, I think our ingenuity and ability to manipulate our environment and the global environment can be turned into a good thing that, in fact, will let us survive.
What do you think, Natalie? I mean, the jellyfish have been around a really long time.
Bacteria rule the world.
Yeah.
Well, you asked, are we looking for intelligent life? I don't know what intelligence is. So I'm not necessarily. I know that's what you guys want to have.
I do too. I want to have dinner with one of these things.
The people who make movies, that's what they want. I'm just looking for life. I just want to know how we got here. I want to know if all life uses DNA to encode genetic information. I want to know what it all means. I mean, we can't know what it all means, but I live my life, I do my profession as if all the mysteries are knowable. So who knows what we might learn and what self-understanding that might give us, and that drives me. I want to put an end to this cosmic loneliness. I think that that's a really profound moment when we can look up in the sky and know that there's other life out there. Just that, culturally, is probably more significant than knowing that we're all made of stardust, honestly. I think that's going to have a really significant impact on society.
I think that's in the spirit of Copernicus, that it's unforeseeable the impact it will have on our cultural thinking. I wanted to, in the spirit of you waxing poetic about the human campaign to know, to understand, to be artful, to be poetic, to be thoughtful, to be curious. I know that you're a big fan of the instruments.
Yes.
Is this Palomar?
Yeah, that's Palomar Observatory in Southern California, about halfway between Los Angeles and San Diego. And you can see that, I don't know if you noticed, the catwalk was right underneath the dome slit that
you
was
mentioned.
closing. Yeah. This is inside the dome. It's a huge dome. It's about 100 feet across. The telescope is 5 meters in diameter, 200 inches. For many years, I think over 40, it was the largest operating telescope on Earth. And there's a little essay I wrote about our ability to do astronomy during the pandemic, and it was published graciously by Scientific American, to bring them back into the picture here, last May. And this is partly film footage from a little movie we made of that essay that's making the rounds right now. But the whole point of it was that we as astronomers are reading the memories of the universe. This is our job. And trying to decode them to understand what happened in the past and how that relates to us. This is something that I've been thinking about for a long time, and I think that's kind of what you were getting at. This is our job. See what happened in the past. How did we get here? How did we emerge? And why? I mean, the why is kind of a philosophical question, but if life is simply a natural outcome of a given environment, that's your why. We're simply a natural outcome of this universe.
And it's a testament to our tenacity to do things like build Palomar. And I know that this will come up, and I know that you've written about this, Rebecca, but there are people who wonder, how can you propose to spend billions of dollars on a philosophical exploration? And I'm not one of those people. When the problems that we're facing here on Earth seem so daunting.
Well, I think there are two answers to that. One is, how can you not? If the question, as Natalie has said several times, whether we are the only form of life in this universe is a profoundly important thing that we must, I think it's a human compulsion to know that, the answer to that. The other thing is these costs are tiny. When I talk about a $50 billion telescope, and there hasn't been one yet, the one that's going up later this year is about 11 billion. And this one, JWST, it will be magnificent. But that 11 billion is over decades. You're talking about a tiny amount of money that each of you is putting in. Yeah, sorry, go ahead.
$1.33 per taxpayer for 20 years.
Yeah.
And
you
it goes
do
in,
that?
not a single person gets that in their pocket.
Right.
Let's be clear. That's jobs, and it's, and
Exactly.
people are working for those 20 years. And Natalie, Lee Billings in the introduction mentioned the Decadal Survey, which a lot of people don't know about. It was just announced on Thursday. It's this program every 10 years to shape the direction of astronomy. It's very smart. It's been 70 years that the Decadal Survey has been?
There have been 7, yeah.
Seven, and it's very smart because it really does shape sort of the direction. And I spoke to both of you on Wednesday or Tuesday, and even you, Natalie, didn't know what they were going to conclude. And how did you feel about the announcement? And tell us what they decided for the Decadal Survey for the next 10 years of the direction of astronomy.
There were, it's hard to know where to start because I know I have Webb behind me.
Yeah, we
and
can
so
start with
the astronomical community does this once every 10 years. The problem, the pickle that we've gotten ourselves into is that these huge flagship missions, like the James Webb Space Telescope, which is the successor to Hubble, they take longer than 10 years to build. So Hubble was conceptualized starting in 1989 before or as Hubble was launching. So right now we're making decisions about missions that will happen not even after Webb, but after the next flagship after that, which is called the Roman Space Telescope. So we're looking kind of way down the road, and a lot can happen between now and then. But at the same time, because they're so complex, we need to start planning. So astronomers spent the last few, 4, 5, I don't even know, I've lost count, years conceptualizing the next flagship mission based on what the most fundamental, pressing, interesting science questions are that we want to answer. One of them is the search for life. And so I was on pins and needles to know if they were going to pick my favorite, which was a concept called LUVOIR, which sounds fancy in French, but is actually a silly acronym. And that's kind of sort of what happened, but they made it smaller, which I'm not super happy about, but they got it to fit within a cost, kind of a reasonable cost. So it's a decent compromise, and it will allow us to detect potential biosignatures on at least, we're estimating about 25-ish, a couple dozen potentially habitable Earth-sized planets in the galaxy, which means, sorry to drone on, but it means that in your lifetime or in the lifetime of your children, we could know of another living world. This is happening. This is not science fiction.
So I put this slide in at the last minute because I was thinking about us as exoplanets. And in the 70s, the Pioneer Plaques were launched on spacecraft. And this is an illustration of the Pioneer Plaques. The idea was to indicate the kind of life that had sent that into space. And it also gave kind of crude diagrams for where we lived. And I think I included this just to emphasize that the most intentional messages we've sent out into space have only gone about, let's call it less than 100 years ago. So that means the distance light can travel in 100 years, 100 light years, which is not very far. It's really...
I mean, they're just now leaving the solar system.
These are leaving the solar system, so yeah, I'm not being clear. These
okay.
are just leaving the solar system, but the first signals we've sent into space.
Yeah, if you look at the history of strong radio transmissions, it's only about 80, 90 years old.
Right. So there are exoplanets within that range.
There are.
It's possible they're getting our messages.
Yeah, and
then
they're
it'll
probably
take
like,
them...
the hell with this, we're not going there.
Yeah. And then it's going to take them 80, 90 years to pipe it back to us, right?
Yeah.
But also, people want to know, and I know this is corny, forgive me for this question, but I think you're both extremely open-minded. Do you think there's any possibility that somebody within that same sphere, somebody, some creature, some entity, some form of life, is actually sending us messages?
Yeah, absolutely. Whether we even know that they are messages, though, is the other question. Right?
Would we recognize them?
Yeah. I don't know if they're sending us messages, but I certainly think that it's possible that there's another species that knows about our presence. I mean, the sun has only existed for half the age of the galaxy. So there are planets, in fact, Kepler discovered planets that are the age of the galaxy itself, where life has had, 11 billion years to evolve. So, and over that time, it's possible that they're conducting the exact same kinds of experiments that we want to conduct, doing the same physics, and they already know about us. So I think that that's very possible.
So, in that spirit, how are we going to know that they're there? It's one thing to discover the planets, and then I know, Natalie, you've thought, and you both have, I know this, thought about, well, how will we know that they're there? Whether or not they're sending us signals. Like, okay, if they send us signals, maybe it'll be obvious, but if it's microbial life, or if it's jellyfish, or if it's dolphins, or if it's the analogs that live in molten iron, what are we looking for and how do we look for it? How do we look for signatures of life that are not intentionally sending us signals?
Yeah, so we are looking for living worlds where life has created a global biosphere. So that means that the metabolisms of the creatures on that planet are putting waste products into the atmosphere, like our trees do, like algae does in the ocean, puts oxygen into the atmosphere, and that is a global signal. We can actually collect light that has passed through an atmosphere of a planet. In doing so, the atmosphere of that planet imparts a chemical fingerprint that reveals the molecules that are present. So if we collect the light, spread it out into a rainbow, and look at it very carefully, we can find those chemical tracers. We can find those chemical fingerprints, know what was in the atmosphere, and in that way, look at the chemistry to see if there's an indication that that's a living world through these metabolic byproducts.
Rebecca, do you think that we'd be fooled by what we're looking at? Would it be easy to be fooled?
Yeah, I think it could be. I mean, you look at Earth as an example where we can actually figure out what the atmosphere was like over its history, not supremely accurately, but pretty well. And only in the past, say, 500 million years or so has the Earth's atmosphere been remotely like this. In fact, if you're a really extreme environmentalist and you wanted to revert the atmosphere to some, pick your point in the past, we would all die. So when you observe a random planet out there, random age, random, location, random star, it may be significantly different, even though there might be life on it. But I think even though I've kind of, been a little rough with this idea of looking for Earth-like planets, you have to start somewhere. And so we say, all right, let's look for something like Earth. At least then we can match it up with what we observe now. But I think in the end, as you well know, Natalie, every planet we see is different. It's going to be very difficult.
There could be, we call these biosignatures, this evidence of life, of a living world. There could be biosignatures that are agnostic to what we think life might be. We can look for disequilibrium chemistry, for example. All the geological processes operate on very long timescales, right? The carbon cycle is a 400,000 year cycle. Seasonal variations due to seasons creating this ebb and flow of carbon dioxide on the surface of the planet. There might be some kind of a time stamp or evidence of a disequilibrium chemistry that tips us off that this is a living world. Or I also think that if I look at dozens of terrestrial-like planets that are orbiting where liquid water could pool on the surface, I'm hopeful that the living worlds are going to stick out like a sore thumb in some way. So yes, there are false positives. There are geological processes that can also build up oxygen in an atmosphere, but we can look at the big picture, understand those geological processes, and guard against those false positives.
I wonder if deep in your heart, unless somebody lands here and talks to us, if you'll ever really believe it. I mean, I think we would probably be pretty easily swayed for microbial life, right? Because we're all primed to believe that that's probably a low bar. But would you really believe the chemical signatures in an atmosphere told you that there was complex metabolic processes going on for complex systems?
Yeah, I think it's hard to make that claim. I mean, a lot of the things that I've worked on in the past are kind of like these giant Jupiter-like things called brown dwarfs. And they have extremely disequilibrium chemistry, wherein you have enormous amount of methane and carbon dioxide and carbon monoxide mixing together. But it's not, when we say disequilibrium, it means that some force, other than just putting these gases together in a box, is changing their relative abundances. And we know that, well, I don't actually know this, but one of these brown dwarfs could be full of billions of farting cows, but I kind of doubt it. It's a gaseous thing. And so whether you can use that to, infer the presence of life is questionable, but I think I think Natalie is right. We will reach a point very soon when we know there's some sort of biological activity on one of these things that is forcing a change in the chemistry of its atmosphere. But in terms of whether you want to eat them or meet them,
Or they want to eat you.
They got to say hi, right? They might want to eat us.
I just, while we draw our thoughts to a close and we are going to approach opening up for questions, just want to give people a sense of the vast scale of things. We've been talking about our solar neighborhood inside the Milky Way galaxy and the hundreds of billions of stars. And there are how many galaxies in the observable universe?
Oh, I mean, we don't even know. Yeah. It's ridiculous.
In just the observable reach,
More than stars in the Milky Way.
more than stars in the Milky Way, and there are more planets in the Milky Way than there are stars, and then there are more planets in each one of those galaxies. And so I wonder how it weighs on you, the idea that those are so out of reach. And I'm also going to show, that's real data, by the way. That was not a cartoon. That is also made by the American Museum of Natural History. These, as Rebecca was mentioning earlier to me privately, this is real data of galaxies. These are galaxies that we observe, but they're blown up to look more beautiful.
Yeah, it looks cooler that way. Space is pretty empty. It's pretty boring.
So you must lament that you will never be able to see the planets in these galaxies, or do you think that's not true?
That's an interesting question. I mean, I haven't really thought about that before, but I guess I would say, well, since we know that physics and chemistry are pretty much universal, that the laws of physics and chemistry seem to work pretty much the same way throughout the universe, the examples that we find here in our solar neighborhood, even, and across our galaxy, we don't even need to look at the whole galaxy, are probably representative of what's going on in other galaxies. But yes, it is really kind of terrifying to think of how tiny we are in this scheme.
And there's the existential dread.
Yeah.
We're not going to beat
Natalie.
the second law of thermodynamics anyway, so, you know.
So you don't lament that you can only look in our neighborhood?
No. If I have to lament something, it's going to be that I will die with more questions unanswered than answered.
I did, right before I wanted to ask you the last question, I this time I'm going to read from it, because, I can't do so well from sheer memory. This is the closing lines of this long and gorgeous, luscious poem by Maya Angelou. She writes, "When we come to it, we this people, on this wayward floating body, created on this earth, of this earth, have the power to fashion for this earth a climate where every man and every woman can live freely without sanctimonious piety, without crippling fear. When we come to it, we must confess that we are the possible, we are the miraculous, the true wonder of this world. That is when, and only when, we come to it." It's
Beautiful.
quite stunning.
Yeah.
And I wonder if, nobody can say it like Maya Angelou, but how has your perspective, which is really what she's talking about, by referring to aloof stars and passing through the casual space and we as people on the small and lowly planet, and yet we're the miraculous, and I wonder if in your explorations, if you feel that your perspective on life has changed through the process of exploring astronomy and exoplanets and the search for life.
Mine certainly has. I think, when I was growing up, you look up at the stars and you think, okay, there must be planets out there. This is not a new idea. But it wasn't known at that time. And fortunately, I got a chance to participate in the discovery of these things. And it makes you start to think about not just like all those galaxies all over the place, but the fact that there are planets all over the place. It makes a lot of our problems seem kind of silly at some level. And yet at the same time, the science is a purely human endeavor. It's something that we created. Empiricism, it's only a few hundred years old. But it is such a powerful tool that we've used. I mean, we wouldn't be sitting here without science. That I feel this strong sense that human beings are doing something very good, even if there are a lot of fucking assholes out there. Oh, sorry.
You're allowed to say fucking assholes here.
Okay. But I think in general, people have a motivation that is good. And we, as a society, we find people to do these weird things that aren't particularly useful. What Natalie and I do is pretty useless. Well, you too. I mean,
I'm more useless than you guys, man. I do black holes.
yeah, but some of the most important things are the most useless. And some of the most useless are the most important for making us human. And I think that poem is marvelous. It's wonderful.
I hear her poem as a big if.
How so?
Well, we are miraculous if we attain those things. And but life is miraculous, this pinnacle. I look at the universe and I see the rise of complexity, and I do feel like we are somehow the pinnacle of that complexity, and I become a biophile, right? I mean, I love life. I can break down into tears staring at a jellyfish. I kid you not. So I'm very moved by the science. I'm very moved by this complexity that has arisen. And earlier we were talking about if the cost is worth it. $1.33, we can joke about that and say, that's not that much money. It is a lot of money. And we can't be flippant about that. And any money that goes to science is cutting some social programs, so I don't really want to go down that pathway. I think that we do this because, as I said before, it helps us to become better planetary stewards. We learn something about the sustainability of life, we learn to appreciate life, and it makes us better planetary stewards. And I think that's valuable. But also, I think fundamentally that understanding is such a euphoric, profound experience. It's really the only thing that unfailingly leads us away from this path of despair and existential crisis. It leads us towards beauty and wonder, and you can't put a price tag on that. So I disagree that what we do is useless. I think that the pursuit of knowledge is fundamentally of great value.
I secretly think Rebecca disagrees too.
Yes, I meant it doesn't get you a better car or a better.
Well, the car is useless.
Yeah, well,
okay, now I get it.
I hate cars, but that's another.
No, I know people are really excited to ask questions. I just want to remind everybody that we are going to gather in the garden and have a reception afterwards. And so I'm going to keep the questions short because I know we've been here a while and people are going to get restless. But before we open it up for questions, please join me in thanking Rebecca and Natalie. So I think we have a mic stand, and I am going to keep it really short, but only because we are going to have a chance to talk afterwards. So we're going to do the corona. What are we going to do? The coronagraph thing? Is somebody at the mic? If you want to ask a question, please come up to the mic.
Hi, I have a question. Thank you so much. It was a really fascinating discussion. I'm curious about what we've learned about planets, such as the molten iron planet. Do we have a sense of dynamics and timescales at which things are occurring there? Or is it still kind of a black box as to what these exoplanets and how they behave?
The lava worlds like Kepler 10b. I mean, we know that they are photodisintegrating. We know that that silicates can actually vaporize off of the surface. We see, if you take that planet and you push it even further towards the star, and there are such planets that we've discovered, we see evidence that they are photodisintegrating because they have a cometary-like tail streaming behind them that is occulting more of the light. So we know that that exists, and we know that planets can meet their demise that way. There are other things that we can say about a planet like this. We know the age of the star very, very accurately. We know the mass and the radius of the planet very accurately. And so we can run models of the planetary interior to know, for example, if it still has a lot of heat inside, and therefore geological activity. But we're also learning you can tune the ratio between magnesium and iron and get a completely different, well, completely different, but you can actually turn off magnetism. You can turn off plate tectonics because you change the interior structure of the planet. So we think magnetism and plate tectonics are actually important for life, and it turns out that they're very sensitive to what the input composition was, the details of it, right? So that means that there could really be a lot of tuning parameters for planetary habitability besides just the presence of surface liquid water.
Thank you. I wanted to ask you if there was a moment in your career that, like, two things. One, that, like, the most rewarding moment, and then another moment where you really thought you were onto something. I liked the part about coincidence becoming relevant. Just kind of like a quiet moment on your own where there was like a gut feeling that you thought you found something you didn't know before.
Do you want me to go?
Rebecca.
Okay. Yeah, there have been a few of these moments. I've been very lucky to have several moments of discovery that, I mean, it's just the most incredible feeling. I'll give you one example. When I first started out graduate school, I was working on a project that was actually at Palomar. And we were looking for these things called brown dwarfs, which are something, the classical definitions between planets and stars. And on the second observing run, I remember being at the telescope and I was working with this guy and we were looking for strange colored things next to stars. And we observed this star. It was already end of the night, and we were tired, and I forgot to write something down in the notebook that we observed the star. So the next day, we did it again, which was a mistake, but then noticed that, holy crap, this thing is really different from anything we've ever seen. And I got really excited, because this, it was not, in fact, what people predicted these things should look like. It was quite different. And I called up my advisor. He happened to be in Hawaii on a different telescope. I said, hey, you got to take a spectrum of this. And he said, oh, you're just a first-year grad student. Man, you know, this is expensive telescope time. At the time, the Keck telescope was, you know, you couldn't, it was very hard to get time on it. And so we waited, and then we waited a year. And in fact, we had to scientifically, but you're sitting on this discovery. You know it's important. And that moment when we went back to it a year later and actually determined that it was in fact orbiting the star that we found it next to, it was just amazing. And I immediately wrote up the first paper at the telescope that night, and I think we submitted it a few nights later. There's a point of exhilaration there, which is very rare. I mean, I think most scientists want it. It's kind of crack cocaine, really, if you're a scientist. But it's not always, not every scientist experiences it, and I feel very special, or not special, but thankful that I happen to be at the right place in the right time. And also, you know, I guess there's some element of skill involved, but let me put it that way.
And Natalie, I mean, for you, I mean, I imagine Kepler might have been like that, but you might have some more sort of personal tale of discovery.
So many. It's hard to pinpoint one, but I guess, I mean, yes, this moment, in fact, when I was an undergrad, I didn't start out as a science major. I didn't really know what the scientific method was, and it took a while for me to find that path. But I do remember sitting down at a computer monitor with my research advisor at the time, and he said to me, Natalie, nobody else in the world has ever seen data like this that you're looking at, and that was a really amazing feeling. So just to echo what you said, but the discovery, so that's all great, and the whole process of learning about Kepler 10b and confirming it, that came in slowly over a year, and every new measurement we got was just fitting like a piece, that satisfaction that you have when you find the right puzzle piece that fits, and that occurred over a year. And that's all really wonderful and what science is all about. It's great. But maybe one thing I would like to share with you is how science really fundamentally changes our perspective. I already mentioned to you that you should go outside and look up at the sky and see the pinpoints of light, not as stars, but as planetary systems. And that is a very personal story to me, because in the first couple of years, we were doing our very first calculations of what fraction of stars actually have planets based on the hundreds of planets that Kepler was observing. And the answer was always coming back that the average number of planets per star is greater than 1. So this was in my mind, percolating, and there was a moment when I was outside at night running and exercising, and I'm running down the street, and in a microsecond I'd look up at the sky, and without thinking about it, it wasn't a rational moment. I was just looking up at the sky, and I saw the pinpoints of light not as stars but as planetary systems. So I had really deeply internalized that fact, and it changed my perspective so fundamentally that I saw my universe in a different way. And that's going to very slowly percolate through the public consciousness as well. And so I hope that by being up here and telling you this story, it will make it go percolate a little faster.
That's, I think, just a beautiful moment to close on. I'm so honored to share the stage with both of you. You're my colleagues, friends, and I admire both of you so much and your work so much. Thank you so much for spending this time with us.
The feeling is mutual.
Thank you. Thank you for coming.